Well, do you want to take over right away?
Yeah. So,
Thanks.
welcome to this session about randomness in games and search. We'll start with the first presentation with Dennis Soemers about anytime sequential halving in Monte-Carlo tree search. You can start.
Yes, thank you. You can see the slides again, right?
Yeah.
Great. So my presentation is going to be about anytime sequential halving in Monte-Carlo research. So this was work that was primarily done by Dominic for his bachelor thesis. Now he moved back over to the US, and I guess he's still asleep.
No, he just joined. I made him
He
panelist.
just joined.
He will be there in a second, I
if you
guess.
switch him to host as well, then I'm
Yes,
doing the
yes.
first part of the presentation anyway, and then he can take over later. Yeah, so this is going to be about Monte-Carlo research. So the commonly used game playing algorithm, I'm sure many of you have seen this algorithm before. It's this search algorithm which looks ahead in this space of states that we might be in and tries to reason about what's the action that I want to take, right? It has these 4 phases, which it operates through many times. We're just going to be looking at the selection phase for this talk. So I'm not really going to explain much about the other 3 phases. And specifically for the selection phase, we're also even going to zoom in and look here at the top part. So we're mostly going to be looking at just the root node even, but in general, if you are in a single node, how do you select which of these child nodes you want to look into next to explore it a bit more thoroughly? A very common approach is this UCB1 approach. It's a multi-banded algorithm. The basic idea of it is it has this exploitation term and it has an exploration term. And so what it does is when you have, if I go back to this root node, it has a bunch of children. For each of these children, it's going to compute a score based on this formula, which balances exploitation of, or which is this idea of I want to pick nodes which I think are really good, and exploration, which is this idea of, if there is a node in my tree which I didn't search thoroughly yet, then I need to put some more attention into that one. So this is what UCB1 does. Now, if you dig into the multi-banded literature, what UCB1 is really designed for is optimizing for cumulative regret. Cumulative regret is it's shown by this equation. The basic idea of cumulative regret is I'm gonna take this term and subtract here this right-hand side. So the left-hand side, this is just the expected cumulative rewards from picking the best arm n times. So that's n times the expected reward from a single arm. And so this is just this kind of oracle idea of this is the best performance that you could have if you knew what the rewards were for each of the arms. But in general, we don't. That's why we have an interesting search problem. Here, what we subtract, this is the expected cumulative rewards from actually following some policy by over the sequence of n time steps. And so what cumulative regret is measuring is just this difference over many time steps. It's the difference between what could I have gotten if I played optimally versus what did I get from what my policy was actually doing. There's also a different notion of regret. It's called simple regret. Now, what simple regret says is I'm not going to look at all these n time steps. So for cumulative regret, I really had this n here and here. I have this sum over n time steps. So this is accumulating the scores, the rewards over all the actions that I take. What simple regret does is it just says I don't care about all these time steps because many of my time steps are just for the sake of exploration, for the sake of gathering information, for learning about my environment. But what I really care about is at the very end, so say after the sequence of n time steps, at the very end, I have one decision point that actually matters. And for that point, I want to minimize my regret. So for this one time step, I want to get a good score. I don't want my difference between the optimum and what I actually expect to get. I don't want that difference to be big. So if I go back to MCTS, I said that MCTS iterates through these phases many times. Through these phases, it's going to gradually build up a search tree. And so while it's building the search tree, it's building the search tree to gain information, to learn about the all the possible future states and the actions I could take and what they would lead to. And the rewards that I collect, like if I search through my tree, I'm just in my head, I'm kind of just simulating phases of play and seeing what happens, what is my outcome if I do this or if I do that. And so in this simulation process, you really don't care about the rewards that you actually get aside from collecting information. What you really care about is at the very end, after you've done your search, after you've run through these iterations, then you're going to make one final, you're going to have one final decision point where you pick an action that you actually play in the real game. And so that's where you really care about your performance. So that's what simple regret measures rather than cumulative regret. So based on these two notions of regret and this idea that especially in the root node of MCTS, we might really care about simple regret more so than cumulative regret. There has been some previous work on getting away from this UCB1 equation, but moving on to different styles of algorithms which actually optimize for simple regret. A common algorithm that does this is sequential halving. So the basic idea of sequential halving is we have our root node, we have a bunch of children. In this case, we have 8 children. And we're going to do uniform exploration over them. So you see this 468 in each of these nodes. We're going to dedicate 468 iterations to every single child node. This is in the first round. After that, we're going to find that 4 out of these of these 8 are better. Like we're going to just pick the best half of the arms that we have. We're going to say only these arms survive. The rest, we're going to get rid of them. Then over the 4 survivors, again, we do uniform exploration. Again, we keep the best half. We let them move on, go to a new round. Again, the uniform exploration. And then at the end, we only have 1 left. This is my best child. So this is how sequential halving basically works, and you can put that inside MCTS as well. And this will, at least theoretically, this will optimize for simple regret rather than cumulative regret. Now, the issue with sequential halving is that we have these 3 rounds here. And specifically in this case, it's 3 rounds because I have 8 arms and I can halve that 3 times. And if I halve it again, I only have 1 left. If you have more arms, you might have more than 3 rounds. But yeah, you have this structure where you have these rounds within which you do uniform exploration. And between these rounds, we also evenly distribute the number of visits. And to do this, we need to know in advance how many iterations can we actually do. And this means that we don't have an anytime algorithm. So an anytime algorithm is one that you can cut off at any time and just say, okay, now stop searching. Now I want my best result. If you stop searching for this one while you've only done 1 round, you will have no idea what to do. So this leads to the main research question that we had in this paper. And after this, Dominic is going to take over to explain the actual work that he's done. So we know there is this sequential halving algorithm, which we might prefer to use in MCTS, but it's not an anytime algorithm. And so the question we want to address is, can we design an algorithm that is anytime, but behaves kind of like sequential halving? Dominic, are you there?
Yes, I'm there. So I'm going to try to be quiet because it's Thanksgiving here and in the US, and it's very early. But so our problem statement was, how can we make an anytime algorithm version of sequential halving? And I came up with the basic general idea and workshopped it with Dennis here, that we can maybe always assume the smallest iteration budget in sequential halving and Monte-Carlo tree search sequential halving, and then iteratively apply sequential halving to the search tree as long as we can. So we just always assume the smallest amount and we just apply it of iterations and apply it in the smallest kind of dosage to the tree and update the tree as we go. So next slide. Oh yeah, the possible consequence of this is it won't be completely uniform or symmetrical, the resulting tree compared to original sequential halving, because sometimes due to this kind of playing sequential halving from the root node and going down, we give the algorithm an opportunity to change its mind in a way. whereas the original sequential halving is mostly deterministic, if not deterministic, depending on your algorithm. Next slide. So here's a kind of diagram. Looks very similar to the previous diagram we saw in sequential halving, but as you can see, we explore every arm at the root once, and then once we can iterate twice more to the next layer and the next layer and the next layer, and depending on your set of arms, you are allowed to do more iterations going down. It's similar to the previous algorithm, but if you go to the next slide, we can see how on a second pass, because that previous slide was one pass, we kind of update our tree and then we look at it again, and then we try, because we have more time in this case, that's why we can do a second pass, going through the tree again. We see that different nodes are valued more, so then we are able to go down that path, and we continue this until we hit an arbitrary stop point, whether that be time-based or iteration-based, and then we choose our best arm that we derived. So then, next slide, please. So for our experiments with this anytime version, we first explored a multi-arm bandit experiment setup, wherein a multi-arm bandit is just a very simplified environment wherein you have K arms, and those arms have are decision points, and those arms have associated means that we have to derive, and we just use the best algorithm at one layer of those decisions to discover those means. So what we did was generate 100 synthetic multi-arm bandit problem, 10 arms, and then discover and see how the algorithms perform on a very kind of synthetic basis. So this allows us to scale up and kind of think about a theoretical maximum performance metric, because when we get to the board games that we're going to test on, there's a lot more variables to take account when comparing algorithms. Next slide, please. Here's our performance. As you can see, anytime sequential halving versus a time-based sequential halving that we also created as an extension, and the original UCB1 algorithm and base sequential halving. Sequential halving, in general, all the sequential halving algorithms perform very consistently similar. And anytime is very competitive with those sequential halving, the original sequential halving variants in this case. Although UCB has a lot of variation and ends up usually being better in lower iteration budgets or time budgets than the sequential halving algorithms. But as we can see, sequential halving mostly kind of tends to stay consistent with its brothers, anytime sequential halving, that is. Sorry, yeah, next slide. So for our board game setup, we would test a MCTS variant of sequential halving called hybrid MCTS that is derived from another paper from our faculty alumni, and then an anytime sequential halving kind of MCTS kind of implementation against UCT over 10 different board games. And we played each game 150 times with symmetric kind of side switching. And they utilize iteration budgets ranging from 1,000 to 50,000. And so next slide. Here we could see some results of the average of all games and their scores at different iteration budgets. And we can see first UCT and anytime sequential halving versus hybrid MCTS, which is the algorithm that anytime sequential halving is basing itself upon to be put into Monte-Carlo tree search. And we can see that both that in some cases anytime sequential halving is superior to UCT when comparing it against the previous iteration of sequential halving. Next slide. We also see, though, that when comparing hybrid MCTS and anytime sequential halving against UCT, which is what we really want, we want to be competitive with UCT in general, because it is the standard. We see that anytime sequential halving holds its own, but hybrid MCTS with its iteration budget, but fixed iteration, uniform iteration budget still is slightly superior. But you remain to say that anytime is pretty competitive. So next slide. So our conclusion is that in a multi-arm banded environment, anytime sequential halving performs similar to sequential halving. But in board games, results can vary. See our paper for this because it's kind of interesting which games are, different in that regard. But averaged over all the games, we can see that it's competitive with UCB1 and isn't superior in some cases at higher iteration budgets we've seen. And it's not as good as HMCTS or standard sequential halving, but it is an anytime variant, and it has a lot of work and a lot of research to be done. So, thank you. That's our presentation.
Thank you for your presentation. So we don't have any questions, so please ask your question on the Q&A section if you want to. Maybe I'll have a first question. When you test on the multi-arm bandits, you choose 10 arms. Do you know what the relation, how your algorithm performs with a variable amount of arms? If you choose more arms, is it as good as with 10 arms?
We didn't test for that, but that is some room for future research. I guess I think we assumed in our experiment setup that it would scale kind of uniformly the results. Although Dennis probably has more experience.
Yeah, so this particular setup is kind of a very, very standard basic multi-arm bandit setup that they also introduce in like Sutton and Barto's book. That's like a very standard kind of baseline. I guess really because here we kind of see everything is worse at the beginning, right? And it gets better at the end. And I guess that really just shifts as you increase the number of arms, and you're gonna need more time to reach similar levels of performance.
Okay.
But I as far as I know, from general trends between say UCB and sequential halving, it's generally the case that for low number of iterations, UCB might be better, but for more iterations, and of course that needs to be balanced against the number of arms. Sequential halving will be better.
Thank you. So we have a question from the chat. In-game playing, search on the move that is ultimately selected is cheaper than search on moves not selected because those evaluations can be reused on subsequent turns, and algorithms vary on how much search on average they get to reuse this way. So how does one control for this during evaluation and comparisons?
Let me read the question again. It's a long question.
Okay. It's in the chat. It's very long.
Yeah, I'm seeing it. So it's in the movie. Is it possible for David to speak up? I don't know if he can be given mic access or if he's even got a mic turned on at all.
I guess this question is really more relevant when you're talking about the anytime sequential halving versus. Oh yeah, you got.
Can you hear me?
Yeah.
Yeah.
Yes.
I'm basically referring to the fact that if you're playing multiple turns, like the agent is playing across the whole game, and you do a bunch of tree search for different moves at the root, once you figure out what move you actually want to pick, and then your opponent responds with a move, there's a good chance that a lot of the search you did in that subtree, like you have those evaluations, you can either carry that subtree directly over, or you have cached evaluations if you're querying a neural net. And so a lot of that computational work can be reused. And so depending on how search balances its exploration and things like that, you might end up with more or less reuse on average with different algorithms, and that affects your the effective efficiency of the algorithm. I'm wondering how can one control for that when comparing between algorithms that do exploration very differently?
Yeah. I get it. I think this is more of a discussion of sequential halving versus UCB than really our specific anytime version of sequential halving. Generally, I would say that sequential halving, it probably does do more exploration at the root. So I guess it also really depends on how big your budget really is. Like in the limit, UCB1 will really concentrate almost everything on the one movement picks, right? Whereas in the limit, sequential halving will still spread around a lot of budget at the root. So in the limit, there's that difference where you would get more reuse out of UCB. Generally, we're not interested in the limit, right?
Okay, thank you.
How that, yeah.
Yeah, maybe you can continue the answer in the chat because we have to move to the next talk. Thank you.
Oh,
so Achille, can you share your screen? Okay, so you can start.
Okay. So hi everyone, so I'm Achille, and today we'll talk about our paper titled Belief Stochastic Game, a model for imperfect information games with known position. So first, a bit of context. So this paper falls into the field of general game playing for imperfect information games. So general game playing is a field of AI in which we want to design an agent capable of playing any game given its rules without prior human knowledge and at a level comparable to a typical human player. So when I say without prior human knowledge, I want to say without any tips given by the developer on how to play well the game. And imperfect information games are just games with some hidden information inside. So for example, card games, you don't actually know the cards of the opponent. So there are some information that are hidden to players. There is actually a few models to model those games. And so the first one I will talk about is extensive form games, which model games as tree. So nodes are state of the game and edges are action. And since there are information that are hidden to player, there are some states that are indistinguishable for players. So for example, in card games, since you don't know the hands of the opponent, there is a lot of states that cannot be distinguished. And so those states are just grouped into what we call an information set. However, in those information set, there is no notion of who knows what, which is actually important for reasoning in imperfect information games. So, for example, you want to in the future when you are sorry. So you are trying to know what the opponent will do in the future, and so for that you have to know what he knows. And often people rely on crafted solution to recover this distinction, but since it's a tip given by the developer for the agent, it is not suitable for general game playing. Another model is factored observation stochastic game, which is based on the concept of observation. So agents don't interact directly with the underlying environment, but observes only their perceptible part of it. And so now the information can be divided between public and private information, but there is still a small problem because agents still need to keep an estimate of what state they are in. And this is done through state estimator that just group together observations into a belief about the current state of the game. But these estimations depends on the game and often lead to uncrafted solution inside the agent. And so this is also not suitable for general game playing. And so what are we really looking for? We are looking for a formal model for imperfect information games suitable for a GGP agent. And so there should be no uncrafted solution that is required inside the agents. And so we came up with a model we call belief stochastic game. And the idea is to simply move the game-dependent state estimation process from the agent inside the environment. And this can lead to a more independent agent, and so the development of a general game playing agent. And so there are still the policy inside the agents, but the policy competition is not necessarily game dependent. And so, yeah, we could try to compute policies for all games. And so now agents receive belief states rather than observations. And so more formally, a belief state is a probability distribution over the possible states of the game, which represents what is the likely underlying states of the environment. And since we are in the general game playing field, we need to find a common representation for the belief state so that the agent can be applied to any environment. But this is not really practical since it's really hard to find a universal representation. And so we can try to just exploit structure of commonly played games. And so we identified two primary sources of hidden information in imperfect information games that humans play. And so the first source is the unknown position of the pieces within the playable area. And so this kind encompasses games such as Battleship or Quickspiel for chess. And the other sources is the unknown value or identity of the pieces. So games like card games where you know where cards are, but you don't know actually their value, or the game of Stratego. And actually, a lot of games human play fall in this category and not the first one. And so now, we focused ourselves on this last category of game. And so now that we know that the uncertainty about the real states only arise because of the uncertainty about the identity of the pieces, we can simply store in the belief states a probability distribution for each piece describing its possible identity. And those probability distribution can just be updated easily by the model by just propagating any updates to a piece to all the other probability distribution. And everything else in the belief state is actually seen by the agents. So everything else is visible in the game, and it is simply stored in the belief state. And so when I say everything else, it's the set of pieces and their position, the graph of the playable area, the agent whose turn it is, and all game variables that are needed for the rules. So for example, the pot in poker or the player's money, etc., etc. So now that I've talked about the belief state representation, I can delve a bit deeper into how the definition of belief state stochastic game. But don't worry, I will not talk about math. I will just point out some important points about belief stochastic game. And so the first point is in the game, we store actually different point of views. And so there are three types of belief states that we store in the game. The first one is the world belief state, which is the actual state of the game. So here, for example, all cards are visible. Another one is the private belief state, which represents the agent's belief about the game from their perspective. So for example, here, it's the belief state for the bottom player, where he can see his card, but he cannot see the opponent's cards. And the last one is the public-private states, public belief states, sorry, which can be viewed as an external view on the game. So it's just an agent that is outside the game and that's seeing the game. And so here, for example, this point of view only sees the cards in the middle. And so an agent that plays the game will only receive its private belief state and the public belief state. And so the world states stay hidden. And so there is a distinction between what information is public and what information is private. Another important point is that legal action functions must return a probability distribution on the actual possible actions. And this is because since the identities of the opponent pieces are unknown, their actions is also uncertain. So, for example, in card games, if you don't actually know the cards of the opponent, and so you don't know exactly which card he will play. And in Stratego, you don't actually know which pieces can move on the board, since there are some pieces that can be a flag or a bomb, but you don't know that. So there are some actions that are impossible, but you have to take that into account. However, from the perspective of an agent, its actions is completely determined just because he knows his pieces, so he knows what he can do. And the last one is the transition function. Since transitions are not always deterministic, due to, for example, randomness in the rules, when you have to throw a dice or shuffle a deck, or also because there are uncertainty about the state of the game. So, for example, when you are playing Stratego and you are attacking an opponent piece, you don't actually know what is the identity of the opponent piece, and so there are different transitions possible. And so we need to keep all the different belief states that are stored in the game. So the world belief states, all the private belief states, and the public belief states consistent with each other. And so to do that, first we will the world belief state is updated by a referee or a game manager, and only one possible outcome is chosen. And then the public and the private belief states are updated by selecting their most consistent transition relative to the world belief states. And so for the two belief states, everything seen by the agents must be the same, and no possibilities in the identities of the pieces may contradict each other. So, for example, in Stratego, if a piece in the world state is the flag, then in a private belief state, the same piece should at least have some probability that it's also a flag. So there are actually some advantages to this model. First, agents are no longer tied to specific game environments. So we could try to just apply them to any environment, since there is no handcrafted solution inside the agent. Another one is that it can help evaluate agents more fairly, since you are just evaluating their policy and no state estimation process or no handcrafted solution inside the agent. And also from the agent's perspective, since the agents know the belief about the game, their perspective is more related to perfect information games, which could help just apply some principle of those type of games. But there is a downside to the model, which is that it increases the computational complexity of the transition function, which could negatively impact the search algorithm for policies inside the agent. And so to conclude, we introduced a new formal model for imperfect information games that exploit the structures of games that are commonly played by humans, and also eliminates the needs of handcrafted solution inside the agent, which could potentially lead to the development of a GGP agent. And in the future, we want to extend the belief stochastic game to different sources of hidden information. We also want to apply the model to wider range of games by also integrating it into a general game playing system such as Ludi. And we also want to experiment with some agents and explore possibilities for the development of a GGP agent. Yeah, thank you.
Thank you, Achille. Please ask your question on the Q&A section. If you are a panelist, you can ask in the chat. I have a first question. So you say that you're giving some probability distribution of the PCs, and for legal action, you said that it should be associated with a probability distribution on the actual possible actions. How this information is just what the how can you guarantee that this information given from probability distribution is just what the agent could compute alone and not some external information that may help him?
Okay, so in the belief state, we store the only thing that is that is linked to probability distribution is the identity of the pieces, and this is linked with only the rules of the game. And so when you are just describing the rules for the game, you are just saying you are just describing how the probability distribution will change, and so there is no human knowledge that will be added to that. And so after that, when you are just computing the actions, you are just searching like for every piece, if it can move, then you can move it. And so you will just check, okay, what is the actual probability that the piece is a type of piece that can move, and it will just use that probability as the probability of the action. And so there is so if you only implement the rules of the game, there is no human knowledge that is introduced. Yeah.
Okay.
But of course you can include it if you want, but it's not. Yeah.
Okay. Well, my main point is just you have to guarantee that you do not cheat.
Yeah. You could, but it's not the idea. So.
Okay. So we have a question from Dennis that he can just unmute himself and ask.
Yeah. So you actually you said that for the actions also you need these probability distributions over the legal actions because you don't know even what actions are legal for the opponent. In the formalisms I'm familiar with, usually we assume that we don't know the legal actions for the opponent. I guess there's also an aspect of like you don't want to need a third-party referee. You want to be able to tell whether your opponent is cheating, and you can't do that if you don't know what actions are legal for the opponent. But I guess that's a matter of representation of the actions too. Like in Strat Legal, I know the legal actions of the opponent in the sense of they can move a piece. I don't know what move they are piecing or what the outcome will be. So do you have any thoughts on that?
Yeah, so the idea, so you don't have access really to what are exactly what are all the so you don't have access to all the possible actions. You just have access to the actions that are possible from your point of view of the game. And so you don't, it's just all the possibilities. Like in Stratego, you can say that all pieces can move, but some cannot, but you don't know that. And so it just, I don't know if it answers a bit your question, but
I don't know, but if you're familiar with GDL2 or GDL Imperfect Information, it is guaranteed that the legal actions that you compute from the description of the game are legal actions. So you don't have a risk to play something illegal.
Yeah. So here all legal actions are actually valid action for So a belief state just encodes a probability distribution on the actual state of the game. And so if the model says that an action has a probability either higher than 0, it just says that there are some states where that action is legal, but maybe not. But maybe the opponent cannot do the action, but there are still a possibility, since you don't actually know what is the state. There are still a small small possibility that the action will happen, but you don't actually know that. So you have to take that into account and just generate all the possible action the opponent can do.
So we have maybe a last question. In this setup, when an agent wants to play out a random game as part of MCTS, do you see this as the agent responsibility or the GGP system's responsibility?
So actually, you can try. So the agent has access to the setup of the game, the initial setup of the game. Since, for example, in Stratego, it's just an empty board and just pieces, and so he can himself try every possible. He can just try random actions. So it's for MCTS, it's more it's more the agent that has to do that. And even for this model, like it's still the agent that has to do his random playouts, but yeah, it's more an agent's responsibility.
Okay.
So the agent has still access to the games and the rules, so he can just try to do random playouts, but he might not test he might not test something that is actually real, like something that is actually the real state, but he could try.
Okay, thank you very much. We will move on the next talk.
Hi.
Hi. So please share your screen.
Yes.
So this is Pablo Ruiz Cuevas, and
yes.
So I'll let you introduce you.
Okay.
About the mathematical analysis of PlaceIt.
Yes. So yeah, let me introduce myself. My name is Pablo Ruiz Cuevas. I will present the solution of the game PlaceIt, and this is a work of Achille, Chock, Bernardo, Subercaseaux, and me, myself. So first of all, 1 second. Yeah. So first of all, we will explain quickly the rules, play the game, and then
we lost your screen.
You lost the screen?
Yeah.
Oh, okay. Just 1 second. It's now.
It's coming.
Working?
Double-clicked on yeah.
Maybe.
I don't see it. Yeah, it says you have started screen sharing, but I don't see it.
Okay, let me do it again. 1 second. Okay, just 1 second. And so maybe
okay.
now
now it's good.
Yeah, so you see the presentation. No? So yes, then we will go through the rules of the game, and we will
just zoom a little bit on your.
Excuse me.
Maybe you're sharing your part of the screen and not the one. So we just see it's too small, so you have to zoom in.
Yeah. No problem.
Thank you.
No problem. Yeah, so we will explain. Well, I start with the rules already. So this is a game about sorting numbers. You are given with a number, and you need to choose in which slot you need to give it a rank. You cannot place the number anywhere. Once you place it, you cannot move it. And the objective is to place all the 20 numbers correctly. So let's quickly play one game so you get what I mean. This is the implementation of the game that Cassie the co-author did. So, for example, you are giving the number 700. This number is somewhat big, so you will know your intuition is that the rank would be high. The numbers are distributed in a uniform distribution between 0 and 1,000. So you would, for example, put it in the 14, no? Because it's high enough but not so high. And then with the 654, it's close to 700. But now you are already in a dilemma. How much space you let between this number and the next one? If you put it too close, then the probabilities of you losing in the next round will be very high. So we, for example, let a space of 2. And then you can continue playing the game just by placing numbers and trying not to lose. You lose when you cannot place a number. So, for instance, here we are also in a dilemma where if we place it in the left, we will have 10 numbers between this one and this one that will eliminate us in the next turn. If we put it in the right, there will be 100 numbers. So clearly, in this case, the 12 is better, but not every decision is so easy. No? So again, with this, if we put it here, there is only 8 numbers that will eliminate us, but this will happen still like around 14 times. So maybe we are tempted to put it in 19, but still it's probably better in the 20. So, and just quickly finishing the game, here we probably would let it some padding. Here, if we place it here, and we are already probably about to lose, because the probabilities of winning this game are not so high. But as you see, like every time the choices that we can make are smaller. Like we have only one choice now. And finally, we lost because the 730 cannot be placed, and we could not rank the numbers. We could not sort them. So coming back to the presentation, more or less, I hope you already got what is the game. Sorry, not the one I wanted to press. Yeah. So let's go with a small introduction on sorting that you already probably know what it is. Or ranking, there is different algorithms for sorting or ranking, and all of them, or typically they have some drawbacks. If you want to sort fast, you're probably also expending a lot of memory. The perfect algorithms for sorting, they require quite important constraints. And in this case, the constraints of the sorting algorithm is that we want an online algorithm that is non-adaptive in the sense that we cannot swap a number once it's placed, and is distribution informed because we know the distribution of the numbers that we are coming. And we want to find a solution for this game. So we will define the perfect strategy as the one that gives us the most probability of winning being like placing the 20. And this is what we will find, the probability of winning PlaceIt. So for building the solution, I want to start solving an easier case where the numbers are distributed from 0 to 1 in a continuous uniform distribution. In this game that it's close enough to the real one, the questions will be a bit easier, and we can build the intuition slightly easier. So, for instance, if we have only 2 slots and we get the number 0.4, we will probably put it in the left because we have a 60% chance that the next number is bigger. And if we put it in the right...
Excuse me, can you just not do in full screen, because some of the screen is not visible. So if you go back and not go to full screen, we can see the entire...
Okay.
Yeah, like this is better. Just make it...
Okay, no problem. So, yeah, no problem. So then if you plot the probability of winning on every choice, then it will be something like this, like in this plot in the right side, where for sorry, we were in this one. So the bigger is the closest the number is to 0.5, the higher is the probability of losing. But at 0.5, we take another decision. So at the end, the probability of winning this very, very simple game is 3/4. And this this can be expressed by these simple equations. If we go to the case where there is 3 slots, then it gets more complicated, but we can still draw these probability choice lines in this plot, and at the end, again, the area will give the probability of winning. But of course, like when you, for example, place the first item in the left one, the probability of winning the right part, like the 2 left, is the probability of having win, like the previous case, like the probability of winning PlaceIt with the continuous version of PlaceIt with 2 slots. So that's why like this plot in the right is scaled to the probability that we just found in the previous slide. So another interesting thing is that we will need to find the thresholds for finding the probability. So if we continue doing this for bigger cases, then we will realize the pattern. The pattern is that we will have the probability once we place a number in the game. We are left with the probability of winning the left game, the game that it's contained in the left of where we place, the right game that is contained in the right of where we place, and the probability of that the numbers that will be given, they are possible to be sorted, which is a binomial distribution. And is the term that is in the center. P0 and P1 is the probability of 0 slots, that is 1, and the probability of 1 slot, that is also 1. So those are trivial cases. And then if we just make it the equations, they will look like this. We will have the sum of the integrals of the binomial distributions scaled by the probability of the left and the right game. And as we know the previous solutions, we can compute analytically the cutoffs of the distributions, which are expressed in this equation in the middle of B. So if we continue, well, this is how these curves drawn by hand would look like in a real case with 7 slots. In the left, you see the probability of winning the game with 7 slots by placing the number on each of the slots. But of course, you will place the number in the best slot, and that's why the probability of winning the game is given by the integral, which is the shaded area in gray. And the important thing is, like, once you have computed these thresholds, these cutoffs once, then you can you have a cheat sheet in the game where you can order each element in constant time, so which is very efficient. And also in this plot you see like the decision threshold, where you will decide to put the item one bucket into another. Another important thing that I didn't mention is that this game in the continuous version is the sub game in the left is the equivalent to the whole game, but scaled by a factor. So you for using this cheat sheet, you need to actually renormalize the game from 0 to 1 instead of, for example, from 0 to 0.3. That is what it will be given in the left, for instance. And we are comparing the optimal solution that is in the right, that is given by your equation, and the naive solution that will be, for example, if you say, okay, if there is 20 slots and 1,000 numbers, I split the 1,000 numbers in 20. We have and we put 50 numbers per slot. This will be in the discrete, but in the continuous you can actually also do the same with 0.2. And there is a bit of difference, but it's actually not that high. And most of the difference is given by the effect of the border. Because if you put a number that is small in the border, the probability of losing it will be very high, as there is a lot of turns, and even and then you actually need to let more space. So, well, lastly, for the continuous version of PlaceIt, the probability, as you see, decreases exponentially, and the probability of winning already with 19 or 20 slots is around 1 every 10,000, which is not much. So, and about the original game is very similar, but has discrete elements. So what we do is instead of taking the number of the element, like the cardinal, we take the number of elements, the cardinality, sorry, for as a normalization. So we say that there is 999 elements as in the original game, and instead of using the binomial distribution, we use the hypergeometrical distribution, which will take into account that there is no replacement. And once we have taken that into account and we have substituted the integral by a summatory, then we can exactly do the same as before and compute the cutoffs and compute the probability, which is 0.013, which is actually very, very small. So winning this game is very, very challenging. And finally, well, we can express the equation in another form that may be a bit more explicit. And this is how it will look, the probability of winning the game based on what you choose. As you see, like if you get a really, really small number and you put it in the first slot, then the probability is the highest because it's the equivalent. If you, for example, get the number 1, then the number 1 is out of the game, and then you end up with 998 numbers or items for placing it in 19 slots. And that is what this curve is giving you. This is saying, okay, if you really got the first number in the first position, then the probability of winning this game is actually the probability of winning the game with 1 slot less and 1 number less. But for the rest, is as you see, you will take just like the small top part of the probability for getting the maximum chance of winning, and there is a small deviation from just like the naive solution in the corners of the game. But aside from the corner of the game, the solution, it's more or less the trivial one. And finally, about the computational complexity, the analyzing, like this divide and conquer strategy of analyzing the left and the right game, it could scale very badly, but we can memorize store and reuse the results. So when we do that, actually the computations are quite fast. It's in order more or less m squared n. And I think if you compute the cutoffs instead of finding them by comparison, I think you can get it also in OMN. Though this is for computing these cutoffs. So actually, when you need to sort the items, you can do it every item in constant order. So at the end, is use ON for sorting. The catch is that, of course, this is a probabilistic sort, and you will end up sorting the full array 1 every 10,000 times, which is not much. Yes. So about how to improve this game, I think 1 in 10,000 is very, very small. For winning this game, you would need to, for guaranteeing that you will win this game with a 99% chance, you will need to play this game like 46,000 times, which is a lot. But you could vary M and N to make this game, like the number of slots and the number of items, you can change them a bit to make this game a bit more playful, enjoyable, or that can be enjoyed better. Especially if you let M and N closer together, the real solution is farther from the trivial one. And if you choose, like in these contour plots, you can choose then number of items and number of slots that gives you a probability closer to 1 in 100 or something that is more reasonable. And then the game will be more enjoyable. And yeah, finally, where to go from here? Well, we could do the algorithm for computing this cutoff better, though once you have computed them, it's enough. And we can explore many subgames possibilities, like instead of wanting to win the game, what is the best strategy for having on average more score, which is not the same as having on average more wins. And yes, like for example, exploring the continuous case is at the limit of the case when there is infinitely many items. But there is a lot of limits that we didn't explore. There is a very another kind of game like this secretary problem that is related to this, where the optimal is, for example, in 1 divided by the Euler constant. We think that the probability, like, we can find something in the limits of this game, but we didn't still find anything like that. And yes, so I'm finding applications, because at the end this is a sorting algorithm that may have application in real life. We think that the most likely applications that this will have is in real systems, where swapping something once it's placed will be very, very complicated. For example, if it has a real weight or something that avoids you to move it. So yeah, more or less that was the presentation. And yes, thank you for the invitation.
So we have a comment from Ian Waters. I thought the probability of winning was low, but 1 in 10,000 is a difficult cell to play. It's very challenging and right. So yeah, if I can if you want to.
Yeah, actually, like, the origin of this game is very funny, because it's I think a TikTok game or something. I didn't know it by TikTok, but it seems like they were increasing the number of slots. They started playing with less slots, and they increased the number of slots. And there was one guy that was uploading a video of himself playing the game one day, like after another, trying to beat the game. And I mean, I think he's still doing it. Probably it will never happen, because, as I said, the probability of him winning is like very, very small, and he may be 46,000 days playing it, and he won the game. He went in, and this with the perfect strategy. With just a random, not perfect strategy, it will be much harder.
Okay, thank you. We have a question from Masgoudry. With your strategy, do you have an idea of what is the median number of moves before losing?
Good question, but no, we didn't compute that number. No, we just didn't compute it. So now I can tell.
Okay, if I can complete. Can you easily derive your computation of probability with the different game when you want to do at least a certain number of placements? Would it be possible? And is it
to modify it for
just to derive your calculations, just to evaluate the probability of almost winning, except such a number of.
So as it is made, we would need to modify it a bit. I mean, I was working in this invariance of the game where I was optimizing for the average number, like the average numbers placed, and the best strategy is actually very similar to this one, but I didn't. It was much harder. So it's easier, like, to find a strategy for winning the game, that the strategy that on average or in median gets the most items. This is a harder strategy to find because at the end this is an analytical solution which can be computed and in terms of simple equations, which is the surprising thing. Because, like, as the sorting algorithm, there are not so many sorting algorithms that are really solved in the way this is. This is, of course, it has very hard constraints, but this is what it made it possible.
Okay, so thank you very much. I think that the session has ended. So we have a 25-minute recess, and we'll meet in 55 minutes with keynote number 4. Thank you.
Thank you.
Yeah, thanks. Thanks to all of the speakers, and thanks for sharing.
Thanks. It was not easy.
No, you did a good job. Very nice.
Okay, thank you.